Okay, coming to the today's class, we discussed in today's class about the viscosity and try to solve some problems. So everyone, I request to keep some papers with you, so to write the questions and answers and to practice some problems today. Now coming to the viscosity, in this we are going to study the Newton's law of viscosity. So Newton has conducted experiments on finding the viscosity of liquids. So how that viscosity depends on different parameters. So that we are going to discuss. And in the last class, I have told you about this experiment. So he has taken two plates. One is the fixed plates at the bottom, another is movable plate at the top. So this I had taken in the last class, where the fixed plate is not moving, is stagnant. So that is showing the bottom side here, the fixed surface, and above which the liquid is flowing, or it may be stagnant up here. After moving this upper plate, I am going to create some flow from this liquid. You can observe in the sketch given here, to move this plate, you need force because fluid cannot flow easily or without any force applied. And for that, I am going to apply some force at the top. And the contact area between this moving plate and the fluid is assumed to be capital A. The area of the plate may be anything, but we are taking the contact area between fluid and plate only. That is A. Area A. So as of this sketch, it is a rectangle plate here. So assume the area. And as the distance y, whatever is maintained between two places, moving and fixed plates, if I go on reducing this plate from this value to very low value, very near to the fixed plate, so what may happen? The force required may be here. Because what happens, whenever the fluid is taken between two plates or any surface rubbing should be happening, what we have to do is we have to overcome the molecular forces or the intermolecular forces, because all the liquid molecules are bound to each other, that molecular on the upper side. And here we assume the liquid is always moving in the layer forms, layer to layer. Like it is making one like a plastic sheet, you can assume, or a glass sheet, you can assume. Okay, sheets, okay, plates, or it is moving like a layers. Between each layer, there is always a molecular forces acting. That force we need to overcome. So that viscosity is nothing but the resistance to flow or resistance to applied forces. Generally, we talk about the resistance of the force or resistance to the applied force is nothing but the property of the liquid, which is due to viscosity. So as I again increase this y distance, this distance between the two plates that go on increasing at very high value, then that force required to move that upper plate will be negligible, because this distance between the fixed plate or fixed layers is very high, and the upper layers of the liquids are connected to the moving plates easily can move. And resistance between each layers will be less at the higher level, but the resistance near to the fixed plates will be very high. So the layer is fixed to the fixed plate. We assume that, and velocity at what it is by applied force at the moving plate, you see, is almost equal to the upper surface of the liquid layer. Is almost equal to movable plate only. So at that velocity is going to be. And in some liquids, we assume this movement of the vessel, it may become collinear or curvilinear. It may become curvilinear or in the curved surface, because it all depends on the liquid what is present here. So about liquids we will discuss later. I will discuss how of the shear stress in the liquids. Why I'm talking about the shear stress, because here the force is applied in the tangential direction to the liquid layers. That's why the force acting on the tangential surface of the liquid, we can call it a shear stress. And for a small layer, if you take the bottom state, you can see here, y-axis distance y is changing. So for a given small layer, I have taken dy. And whatever the velocity change is there between these two surfaces of the one given layer of the liquid, that I can consider changing velocity of the given layer, the, the x-axis. Change in distance is taken as dy. And if you see the bottom layer of the liquid and the top layer of the liquid, then which layer if I consider u as a velocity. Upper surface of the same liquid layer to consider, that is going at very higher velocity at above layer. So that will be the addition of this u, whatever the change in velocity is same. That addition of velocity I will add with the earlier velocity. So that will become u plus du. So like this, we have taken the for small area, we are going to derive this, or generally we can write for the complete
Excuse me, sir. Excuse me, sir.
viscosity. Yeah.
The voice is breaking a lot, so we are not getting the point.
Okay, up to what you have understood now.
Nothing, sir.
So nothing, sir. So from start, it's breaking a lot.
Yeah. Then you would have stopped me earlier. No? Wait.
Sir, I thought it's my net issue. Then later read it's about everyone.
Okay, now the voice is clear.
Yes, sir.
Yes, sir.
Okay, give the reply in the chat box. Shall I continue with the same thing now? Voice is clear now? Okay. See, if any problem is there, you just unmute in between and give the reply. Don't wait for the more time. Okay, within that time, you just reply me with unmuting the mic. Okay. Today we are discussing about the viscosity. So for viscosity, we have taken this Newton's law of viscosity as an experiment, what Newton has conducted. So in that, what he has done is, he has taken this movable plate above the liquid volume, what is considered here for the experiment, and a fixed plate at the bottom. So fixed plate is not moving. So at that point, or the fixed plate position, whatever the layer of liquid is attached, that is not moving at all. So that velocity we are going to consider it as zero velocity at the fixed plate, or the liquid which is in contact with the fixed surface. The velocity will be almost negligible or zero. And as you move this moving plate, which is kept at distance y, for example, this movable plate, if I move, so for moving this plate, I need some force to overcome the viscosity of the liquid. Means the viscosity is nothing but the resistance to the applied force. So whenever you take any fluid, it will be having some resistance to separate from each molecules, or else to move with respect to other layer, it will be having some resistance. That resistance we are calling it as viscosity. So I need some force here. Without force, I cannot move the moving plate. It will be stationary. So once I start moving this plate at given force, this plate will move at a given velocity u. And we assume that the layer of the liquid which is in contact with moving plate also will be moving at velocity u. And in between these all the layers are rubbing each other to overcome the molecular or cohesive forces. Okay. So to overcome that cohesive force only, we need to apply this external force. Also, you can see that is also dependent on the surface area. So surface area which is in contact with the liquid, or this moving surface, that area we have to consider. So area, as it increases, the force also increases because the surface area will be more. If the surface area in contact will be less, then the force required will be less. Simply move the movable plate, then the resistance force will be very high because very near to the fixed plate, these layers of the liquid will be moving at very low velocity, and high resistance to y as high as possible. Then only the bottom side layers of the liquid which are in contact with the fixed plate will be not moving properly. But the layers very near to the moving plate, which are at very high distance, that can move easily because they are not connected to any fixed layers or the fixed plates. So like that, in the right side sketch, if you see, they have shown the zero velocity at the bottom, higher velocity at the top, and layers of the liquid, if you see, they are moving at a different velocities with increasing profile. And if the fluid is idle, it can move in linear direction. Without a Newton fluid, it may become a curvilinear path. So velocity, if you see, and it will achieve the given velocity of the moving plate. And at the bottom, you can see for a given layer, if you want to derive or check the equation. So here we have taken one small layer between dy distance. Okay, a small layer from this upper sketch we have taken and analyzing as dy distance, and the velocity between any two layer surfaces, if you see, that we are writing du. And the bottom layer and the top layer, the bottom layer is very near to the fixed plate, the velocity will be lesser than the upper surface. So that I am writing u, that I can consider it as u plus du. I hope this experiment or the given sketches are clear to everyone. So please comment in the chat box. Okay. We are taking this shear stress because top movable part. So this shear stress contact area, and that can be written as a proportionality, or it is proportional to velocity, and it is inversely proportional to distance y. So as I told you, as you go on increasing this y, the force required to move the plate will be less. As I decrease this distance y, means I resistance will be more. So that shear stress or the force will be inversely proportional to the distance y. So that I have written dy or u by y. For a given complete volume of the liquid, if you take, it will be u by y. For a small layer of liquid, it will be du by dy. So whatever it is, the proportionality is required, means at what force I have to apply the shear stress or I have to apply the force, that will be decided by this mu. So that coefficient of viscosity. So this coefficient of viscosity is nothing but the viscosity or the resistance required to overcome the liquid flow. There, the force is directly proportional to area. Now here, area is what? Area of the surface, which is in contact with liquid surface and the movable plate. So that area we are considering. And force is also proportional to velocity. In the sense, after applying the force, if you see the velocity, that velocity is proportional to force. Means if you apply more force, velocity will be more. velocity will be less, directly proportional. But distance, if you see, the distance between the two plates, if I increase, then force required will be less. If I decrease the distance, force required will be more. So force is inversely proportional to distance y, as like shear stress. Now combining these force equations, I can write it as force is proportional to area of the area in contact with liquid and movable plate, and u by y, means force is proportional to area velocity and inversely proportional to distance y, or distance between the plates. Now if I take the force by area is nothing but the pressure or the stress is nothing but equal to mu. So mu is what again? It is for the, just to make it constant or the equal to sign, that is constant of proportionality. Mu we have taken, that will become u by y. So either you can find the viscosity by this relation or by this relation, depends on the given data in the problem. So data may be given to ask the viscosity using shear stress, you can go by this. Or if the shear stress is not at all given, you can relate these two equations. Mu into u by y, F by A equal to tau. So that tau will be nothing but shear stress. So either by using these two formula, one can solve the different numericals. So these words are nothing but the shear stress is denoted by tau. Then du by dy is nothing but the shear strain, we are calling it as, in the fluid, or it is also called as velocity gradient. Okay, so velocity gradient is what? This change in velocity with respect to distance or per unit distance. That velocity we are calling it as velocity gradient. Then mu is constant of proportionality, is also called as coefficient of viscosity, or generally called as dynamic viscosity many times. Or in the problems, if they ask only viscosity, you have to find the dynamic viscosity. Or so finally, if I write the equation for viscosity or the dynamic viscosity, that will be mu equal to tau. Okay, mu equal to tau into dy by du, or I can like this, which is shown in the red box. That is denominator, that is du by dy. So by this formula, one can find out the viscosity. So one can note down these equations, how we are finding, or if the force and area is given in the problem, you can find by this mu equal y by u in the above equation with respect to force. If you find, that is mu equal to F into y divided by A into u. So either by any equation you can find out the viscosity. So these points. For everyone, the voice is breaking. Okay, now the voice is clear. Okay, later we'll check in the video also whether the voice is breaking continuously or not. It is clear but distorting a lot. So what I can do now with network? Tell me by unmuting the mic, what is the equation for viscosity? Yes.
Tau by du by
Have you noted down the
dy.
equations? Yes.
Yes.
Okay, we'll take the next part. We'll see the next class. Okay. So this viscosity is measured in various forms, and viscosity, if you is proportional to temperature for the liquids. As you increase the temperature, the bonding between the molecules will reduce, or the volume of the liquid increases. So that what will happen, the resistance or the viscosity value will decrease for the liquid, and easily it can flow. And for this, one example you can take is the coconut oil. So as if you see, at lower temperature it may be semi-solid form. At a given proper conditions, it may be in the liquid form. And once I start increasing the temperature, the fluidity of the oil will increase. But for the gases, if you consider, the viscosity is completely opposite, because the gases are moving not with the bonding between the molecules. It is the movement between the molecules, or the molecules are changing their paths or continuously excited in the gaseous form. And once you start increasing temperature or pressure for the gases, still the molecular activity increases, so that viscosity increases, because all the molecules will come together at high pressures and less volume, and it will start to increase the viscosity at very high temperatures. And if you see the units here, so mu I can write it as tau divided by du by dy. So shear stress, and this du by dy, if you see, it is nothing but the meter per second du. So that meter per second is taken here. Dy value meter is taken here. Okay. So shear is in meter. Du is meter per second. It is written reverse because of the reciprocal seconds per meter. So we can cancel meter and meter here. It will become Newton second per meter square. So unit of the viscosity in SI unit is Newton second per meter square, or you can call Newton per meter square. Also in SI MKS unit, you can write it as kg for second per meter square, or in CGS units centimeter square. So in the CGS unit, whatever this dyne second per centimeter square is written, this is called as poise. So one poise is nothing but 0.1 Newton second per meter square in SI unit. If you write it in centipoise, nothing but 1 by 100 poise. So 1 by 100 into 0.1, if you multiply, that will become again in Newton second per meter square. So this will discuss in the problems again. Next point is the dynamic viscosity, sorry, kinematic viscosity. So kinematic viscosity is just a ratio of dynamic viscosity with respect to mass density rho. So mu by rho is what? Dynamic viscosity divided by density value. Now if you check the kinematic viscosity new units, so it's denoted by new here. Units, if you check, the dynamic viscosity is meter cube above, so that we can cancel this meter square and meter square at the upper side. So we have left with what? Kg, sorry, Newton second meter per kg. Now we know that the kg can be converted into Newton. So once we try to convert this into Newtons, we have left with kg second meter. Okay. kg second meter divided by kg into meter per second square as per the given kg if you convert it into newtons. And in this case, we can cancel this kg on the top side. So once you are left with meter square second per second square. So what I can do here, second can cancel and meter square will be left as it is. So finally the unit will be and as the name itself indicates, the kinematic deals with only the velocity, acceleration or the directions, forces, only the time and the distance at what it is traveling. Is that clear? It is not containing any force viscosity. Can be written in Stokes in CGS system, or it can be written in centi-Stokes also, 1/100 Stokes. And here, 1 Stoke is nothing but 1/100 square, 1/100 square meter square. Yes, kinematic viscosity definition is clear to everyone. You can put a message here. So now audio is clear. Is my voice is clear now? Okay. Now it is clear. Yes. So, so now by understanding this equation of the viscosity, the experiment what Newton has conducted and found out the equation that also we know now, tau equal to mu into du by dy. So now if you try to define it, it states that the shear stress in a fluid element or the fluid element layer is directly proportional to the rate of shear strain So rate of shear strain is the velocity gradient. You can write proportional to the velocity gradient also. It is proportional to shear stress is proportional to the shear strain or velocity gradient, and the constant of proportionality is called as coefficient of viscosity. Also, these fluids obeys the relation, or whichever the fluid obeys this law is called as Newtonian fluids. Okay, it should be proportional to shear stress, proportional to distance, and it should be inversely proportional to velocity. So if the viscosity is obeying these relations, we can call it then we can call it as non-Newtonian fluids. So now we will see how this Newtonian and non-Newtonian fluids behave. So here the list of fluids are given, types of fluids are given. So this I can take in PPT here. All of you can see the PPT. The slide is visible to everyone. Okay. Yes, dynamic viscosity I'll once again explain to you. Okay. Just a minute. Delete this. So if you see this graph, in upon the viscosity. On the y-axis, they have taken shear stress or the stress values in Newton per meter square. The tau value they have shown. On the x-axis, they have taken the shear strain, or the strain is nothing but the du by dy. And if you see the different liquids, so first I'll go for the Newtonian fluid because we have discussed the dynamic viscosity just now, and we know how the Newtonian fluid should obey the law. Now, if you see the Newtonian fluid, it is proportionally increasing as the velocity gradient increases, or as the shear stress increases or the force increases. The what will happen? The property of the fluid is behaving as per this line. So as the velocity gradient increases, the shear stress requirement is also increasing. And we have different types of fluids here. Elastic solid is there. Okay, so it is not at all changing with the velocity gradient, whatever the stress you apply until some limit. And the plastic material or the semi plastic materials, if you see, up to some stress, it will not change its dimensions, or it will not move with respect to the forces. But after yield stress, it will start bending or changing its fluidity. So after or it is changing it. So similarly here, if it is not proportional to velocity gradient or the shear stress, then what will happen? This will behave like a non-Newtonian fluids. Then we have thixotropic substance is nothing but the jelly-like substance, or the example you can take sauce in the home. You can take the sauce. It is not completely in the liquid state or in the not in the completely solid state, in between. So that will behave like this. It's not directly proportional, but it is curvilinear. So even this dilatant fluids, which are completely non-viscous or very dilute in nature, such fluids we are calling it as dilatant. And one more last is given, ideal fluid. So ideal fluids are nothing but still the viscosity is very less, such that there is no viscosity at all. We cannot talk about the viscosity at all. It is zero. Those type of liquids are called as ideal fluids, where viscosity is completely zero, without applying any forces, without applying any shear stresses, the fluid naturally flows as it is, because it is not having any contact with the surfaces, it is not having any molecular cohesion forces. Easily it can move anywhere, like a gas at lower temperatures. Gas at higher temperature, if you take, it will be high viscous. So these are the examples. So again, we'll come back to this notes and we'll observe. So we have ideal fluids, real fluids. So real fluids are nothing but the non-Newtonian fluids almost. Then Newtonian fluids, we have non-Newtonian fluids, ideal plastic fluids are there. Then thixotropic fluids, etc. or ideal fluids. And here coming to the ideal fluid, which is having zero viscosity, these are incompressible in nature. Okay, maximum times these are the incompressible. We cannot change its dimensions by compressing or decreasing or increasing volumes. We cannot change the compressibility. And real fluids possesses viscosity which are little bit higher than the Newtonian fluids. That is one thing, which are in curvilinear in proportionality with respect to velocity gradient and the shear stress. And Newtonian fluid, if you see, it will just obeys the law of Newton. Whatever the Newton is explaining the law for a given fluid, call it as Newtonian fluids. Then non-Newtonian fluids, if you see, this is the real fluid, as I told. So real fluids and non-Newtonian fluids almost same. By shear stress is not proportional to velocity gradients. It is having the curvilinear path. So such type of liquids we are calling it as non-Newtonian fluids. Now comes the ideal plastic fluid, as I told you, to deform or to start the flow in a given material, if it requires some minimum force to overcome the dimensions or to overcome the flow, that force we are calling it as yield force or the yield stress. So once the yield stress is crossed, then it will start flowing. That is called as ideal plastic fluid. So until that part, it has to overcome the resistance to change the velocities. So like a very heavy viscosity fluids or the industrial sludge or the waste, if you consider, you have to apply maximum pressure, and once it crosses some limit of the given stress, then only it will start flowing. So this graph will indicate you what type of liquids are possible. Change in the dimensions, no flow is solid, but even ideal solids also have some yield stress. So at a given point it may break or it may start acting like a plastic body. So that also depends. So I hope the graph is clear to everyone. The shear stress, if it is proportional, it is a Newtonian fluid, otherwise it will be different fluids. Yes. Now we'll go back to dynamic viscosity once again. So shall I explain this once again? The change in distance, velocity gradient and shear stress, how it going to behave with Newton's law? Is it required or? Okay. So as per Newton, he has taken two plates. One is the fixed plate at the bottom, one is the moving plate at the top. So 3D sketch I have shown earlier that you can imagine. Now any fluid, if you consider, generally it is having some resistance to flow, because here we are not. To start the flow between the liquids, we need to apply some force, and the force applied here at the top, if you see, it is a tangential in direction, so we are calling it as shear stress. So force applied per unit, and the velocity gradient or the change in velocity is also proportional to force. As you apply high force, there will be high flow rate or the high movement of the liquids, and if you apply the less force, it will be less. The velocity obtained by for a layer of the liquid, the change in velocity as du, small change, and the distance change or the y distance between the small layer, we have taken dy for the small layer, and we assume here liquid is also flowing in the layers because of the. Try to write it in the form of equation. I can write it as one side on the red color we can see written in the red color, that is force is directly proportional to area. So how much of area is in contact with the liquid, that much force we have to apply. One thing. One more thing is velocity. And also distance, if you see, as the distance reduces, the force also increases because of the fixed plate or the non-moving layers at the bottom. So that is F is inversely proportional to Y. And if I combine all these proportionalities, I can write it as F equal to mu into AU by Y, or F by A equal to mu into U by Y. For the entire thing is the shear stress in the tangential direction, what is applied by the force per unit area. So that is also proportional to velocity gradient. And to overcome this proportionality constant, we are applying this dynamic viscosity or the coefficient of viscosity. So by this equation, one can find out viscosity value. As per this law, I assume that viscosity is not known to us. To find that viscosity, I can write mu equal to tau into dy by du. Or I can write like this, mu equal to tau by du by dy. So I hope this point is clear to everyone. How we are finding this dynamic viscosity or the coefficient of viscosity. Yes. Yes, all are attentive or no? Or left the meeting? The internet there. And I'll check also the video. If the video is clear, I think network is a problem with your side. Okay. We'll stop the session here. First session. Next session will start at 11 with some numericals. Shall we continue? Okay. So next we'll see how the liquid and gases viscosity will affect. Okay. Just by taking an example, don't write it. You can write the equation, but the problem is not necessary because in this subject we are not discussing about the gases. So just for information sake, I have taken these points. So variation of the viscosity with respect to temperature in liquids and in gases we'll see. So liquids, it will affect with respect to temperature. If you see here, we have to consider two constants of the given liquid. Okay, and a standard viscosity for the water, that is mu naught. So mu naught for the water, if you see, it is 1.79 into 10 raised to minus 3 poise, and alpha beta constants for the water are 0.03368 and beta is 0.000221. So these values are required to find out the viscosity of any liquid at a given temperature. So temperature value, if you know, alpha beta value, if you know, and the viscosity of the water as a standard liquid, if we know, one can find out the viscosity. And viscosity, if you see, it is inversely proportional to temperature here. As per the generalized equation, if you see, mu naught into bracket 1 divided by 1 plus alpha t plus beta into t square. Okay. This equation, if you just observe and check the proportionality, temperature is inversely proportional. Means, as you increase the temperature, the viscosity value is going to reduce for the given fluid. Or the viscosity value, if it is very high, means what will happen? The temperature value may be less. Means how it is dependent on temperature. For that, I have taken this equation. For gases, if you see, just for information I am telling, for gases, if you see the equation, in the gas, the atmospheric air, we are taking it as a standard fluid or gas. So that viscosity is given. Alpha beta constant for the air is also given. So will not bother much about how these all things are calculated. Just we concentrate on the equation for the gases. Now if you see the equation, viscosity of the given gas is proportional or directly proportional to the temperature. That is mu naught plus alpha t minus beta into t square. So this equation and liquid viscosity temperature relation, if you see, in liquid it is inversely proportional. That's why as the temperature increases, molecular bonding will reduce and viscosity of the liquid is also reduces as you increase the temperature. But for the gases, as you go on increasing temperature, molecular activity in the gases will still increases and viscosity also increases. So that the force required to move the gases or the layers of the gases at very high temperatures is very high. Okay. Or you can take the examples in villages. If you see the gases coming from small burner, if you see the gases are coming out with very high velocity without any disturbance or without any problems. Okay. But if you see the same gases coming from the chimney or a very high tower or very high long pipe from the thermal power plants or any big plants, if you see, those gases will look like they are moving very slow. So that is possible only because of very high temperatures. In the plant, if the temperatures are very high, the burning temperatures are very high. In such cases, if you exhaust those gases at very high levels of atmosphere and other things, so there what happens? The velocity of those gases will be less. That is due to high viscosity of gases. Okay. We will take some simple numerical so that even those who have not understood the basics of the dynamic viscosity, in the problems one can understand the equations and how to find this viscosity. Okay. So take down this problem. First problem with respect to viscosity. So here the question asked is, viscosity of water is 0.01 twice. Find its kinematic viscosity and dynamic viscosity in SI units. If the specific gravity is 0.998, so specific gravity don't have any units, okay, and for the specific gravity they have given for a given liquid like water, and one should find out the density of the other liquid or weight of the other liquid by the specific gravity relation. So in this problem you have to focus on the viscosity values. One is dynamic viscosity that we have found out by the derivation from the Newton's law. One more equation is the kinematic viscosity that we have found out from ratio of dynamic viscosity to the density or the mass density. Now first thing is, directly one can find out viscosity because viscosity is nothing but the dynamic viscosity of water is directly given as 0.01 twice. So as I told you, 0.01, if you multiply by 0.1, it will become the Newton second per meter square value. So 0.01 twice I can write it as 0.001 Newton second per meter square. So in this problem, no need to rewrite the shear stress or the force relation with respect to viscosity or the relation with the velocity gradient. So directly viscosity of the water is directly given here. So that we have written in the terms of SI units, that is 0.01001 Newton second per meter square. Then kinematic viscosity I need to find out, because as per the question I'm going, as per the question kinematic viscosity also we need to find out. So I'll write nu equal to ratio of dynamic viscosity to density. Which density we have to take now? That is the question. Either if you take the mass density, the unit will be meter square per second. If you take the weight density, the units will be different. So for this meter square per second, as per the SI unit, I'll consider the mass density. Now for mass density to find out, we know the relation of specific gravity and the mass density, because viscosity and density we don't know the relations, but we know the relations between specific gravity and or the relative density and the density values. So I can write it as S equal to density of the given fluid to the standard fluid. Okay. So if I go by that, density of the given fluid, nothing but water only. But here if you see the value of specific gravity, it is given as 0.998. So as per these values, the mass density, how much it will be now? As per the given specific gravity with respect to required fluid, that is 998 kg per meter cube. What we are doing, the density of the required fluid we are finding by multiplying 1000 into specific gravity, that is 0.998. So now I can take this density of the liquid and dynamic viscosity which is converted above, and I can find out the kinematic viscosity of the given liquid or the water itself. That will be around 1 into 10 raised to minus 6 meter square per second. So just one of you check 0.001 divided by 998. And 998, what you have to do? It is in kg per meter cube. You have to convert it. Yes? So one of you can tell me how to convert it. Rashmi?
Yes, sir.
Yeah, my voice
Yes.
is clear.
Yes, sir.
Okay, how to convert the kg into Newton now? Because we cannot take the ratio directly.
Yes, sir.
How to convert kg in Newton? Yes, Sami.
Sir, uh,
Sami, can you answer? kg force. Okay, whatever it is in, how to convert that in newtons? Like kg force is mass. Kg force is mass or this one. Just multiply by 9.81. So if I multiply kg with 9.81, whether it is a mass or weight, yes.
Mass, sir.
So here in this problem, you have to convert that density value 998 kg per meter cube into mass. So you have to multiply this with 9.81 in the denominator. Viscosity is already in Newton second per meter square. Now if you take that ratio, I'll get 1 into 10 raised to minus 6 meter square per second is the kinematic viscosity. All of you write down this problem. I'll give 1 minute to copy it. So once you have written, please reply. Yes, all of you understood this problem? One is converting the units watts to Newton second per meter square. One is taking the relation with specific gravity and trying to write the density in terms of given specific gravity. What is the density of water? Because everyone knows it, density of water as a standard condition is 1000 only. But here, specific gravity is not given 1. That you have to understand. It is 0.998, almost near to 1. It is given as 0.998. So according to that value, now density of this given water is 998 kg per meter cube. So later we found out the kinematic viscosity by taking these ratios and converting kg per meter cube into Newton per meter cube. Yes, we can also write Newton in kg meter per second square. Yes, we can write. Here in the problem, what you do is Newton you write in kg meter per second square. Okay, viscosity you convert that into kgs in terms of kgs. Kinematic viscosity also you take mu as well as density in kgs. No issues. Answer will be meter square per second. No problem. Shall I move to the next problem? Yes. So in the next problem, I'll read the question here first. You'll understand what is given, what is asked. A plate at a distance. Now comes to the Newton's law. A plate at a distance 0.0254 mm, okay, from a fixed plate moves at 0.61 meters per second and require a force of 1.962 Newton per meter square. Area of plate. Okay, Newton per meter square area of the plate. Determine viscosity or the dynamic viscosity between plates. So this is nothing but the experiment of the Newton itself. What they are doing, they have taken two plates. One is fixed plate at the bottom, okay, and moving plate at the top, which is at a distance of 0.0254 mm. And top plate of the moving plate, we are moving at a speed of or the velocity of 0.61 meter per second. And to overcome the resistance of liquid or to overcome the viscosity of that liquid, we have to apply the force of 1.962 Newton per meter square. Okay, means this is nothing but the shear stress what we have to apply. That is the tangential force applied on that liquid surface is 1.962 Newton per meter square area of the plate. Now you need to just find out what is the dynamic viscosity of this liquid or between the plates, whatever the liquid is there, that viscosity we need to find out. So the sketch is made here. Y is 0.0254, U is 0.61. The equation you can write either two forms. First form, what is written here is the shear stress is equal to viscosity into velocity gradient du by dy, or you can write tau equal to mu into u by y, assuming the complete liquid volume itself is a layer. Okay, so what we'll do is we'll just substitute the values in the SI units. 1.626 to 1.962 is in Newton per meter square, so already in SI units. Mu we don't know, determine mu is given. Du or the change in velocity u is 0.61 meter per second in SI unit. Distance given is 0.0254. This we need to convert in meters because already the force is shear stress is in Newton per meter square. Velocity is also meter per second, but the distance is in mm. So mm, what I'll do is I'll multiply by 10 raised to minus 3. It will be in meters. So once you substitute these all values, one can get mu value. So how much you are getting by this equation? Just check. Mu equal to 1.962 into 0.0254 into 10 raised to minus 3 whole divided by 0.61. So you'll get the dynamic viscosity or coefficient of viscosity. So Newton has given this law to find the coefficient of viscosity. .169 into 10 raised to minus 5 is 0.0816 into 10 raised to minus 3, correct? We'll check now. Yes, 8.17. Just one next decimal you have taken. 8.17 or 16 into 10 raised to minus 5 Newton second per meter square is the unit of dynamic viscosity. Have understood the problem? Just by one equation, just by applying the Newton's law itself, because the statement itself is a Newton's law of viscosity. Two moving plates, a fluid is kept in between. One is moving, one is fixed. Distance is given, area of the plate is given. Sorry, area is not given here. They have given in terms of shear stress. If they have given in the form of force and area, then we would have taken F by A. We'll take the next problem. Now voice is clear. Whatever I'm talking, the voice is clear to you. Okay. Shall you go to the next problem? Yes. Okay. So next problem. So first I'll read the question and we'll understand what is given, what is asked. So this is a question given here. A plate having an area of 1 meter square. Now see here, area is given. A plate having an area of 1 meter square, unit area, is dragged down on an inclined plate. Yes, now see, earlier we are talking about the flat plates or the horizontal plates, but now it is dragged. A plate which is kept in inclined position, it is dragged down on an inclined plate at 45 degrees to the horizontal with a velocity of 0.5 meter per second. So here velocity is given, angle is given. We'll see what to do with the angle. Due to its own weight. Now see here, we are not applying any force on it. Only due to its own weight, a plate is kept in the inclined direction, maybe above the liquid, because below a viscosity something is given. So above the liquid, the plate is kept at 45-degree inclination with horizontal, and by its own weight, 1 meter square metal plate or whatever the plate is there, it is moving it by its own weight by 0.5 meter per second velocity. I hope everyone is understanding the problem. Only thing is what they have done, they have included the angle in this problem. There is a cushion of liquid. Yes, means cushion means the in between the plate there is liquid of liquid 1 mm thick. The height y distance is 1 mm thick between the plate. Liquid is there. That liquid height is 1 mm thick between the inclined plane and plate. Means inclined plane is moving at a fixed. Inclined plane is fixed. Plate is moving downside. So there are two planes now again, but both are in the different inclinations. If the viscosity of oil is 0.1 Pascal second, so Pascal second is nothing but what? Can anyone tell me what is Pascal? Earlier we have discussed what is Pascal. Yes. One of you can unmute and tell me. Yes, very good. Newton per meter square. Unit of pressure, correct. Pressure unit in Pascal, correct. So here what they have done, they have taken written the viscosity in terms of Pascal second is nothing but the Newton second per meter square. So Newton second per meter square is given means it is the dynamic viscosity, or it is the coefficient of viscosity, or it is generally viscosity. So we cannot consider this as a kinematic viscosity. That is one of the understanding. Now finally what we need to find out is find the weight of the plate by which it is moving at the inclined plane. Now in such situation, area is given, so I can take the equation F by A equal to mu into U by Y. I hope this is understood to everyone. F by A is nothing but the shear force or the pressure. F by A, mu into U by Y. U is given, distance is given, viscosity is also given, area is also given. Only thing we need to find out is force. And that force is nothing but what? It is the weight of the plate itself by which it is moving downside. The plate itself is applying the force on the liquid because of its weight. Yes or no? Because by our own weight, I can apply the pressure on the ground while walking or while running. That is nothing but the force applied only in vertical. So coming to the analysis, I can draw the sketch like this with the horizontal plane, 45-degree fixed plate I will consider 45 degree. Plate is also moving in 45 degrees. and in between there is an oil of thickness 1 mm. Velocity is 0.5 meter per second square. Viscosity of the oil is also given 0.1 Pascal second or 0.1 Newton second per meter square. Now, if you consider the weight of the plate, so as they are asking, you find only the weight of the plate over. Don't focus on all these parameters given. So if I want to find out the force by the plate or the weight of the plate, if I consider that is acting downside, so that is shown there. So one can find out the force by using this relation, because here we know the angle, okay, and we know the weight is given or not. Weight of the plate is nowhere is given. Means what we can do here, cos 45 is known, but what about the W? Yes, W is not known, still we need to find out. So keeping that W as unknown only, what they are doing, only cos 45 they are finding because of the adjacent and hypotenuse lines which are known, assuming that angle is given, so we don't need the length of the lines. So F will be 0.707 into W. And conversion of that Pascal is given at the side, that already we have discussed. And next step, if you see, to find the weight of this, as I told you, shear stress I can write it as F by A. So assume I'm writing F by A equal to mu into U by Y. Is my voice is audible clearly? Okay, thank you. See here, in terms of tau, what I told is F by A I can substitute because area is given here. Mu is given, U is given, Y is given. So F by A, what I'll do here is force per unit area. So force we know. Force is 0.707 watt. What is the area of the plate given? Can anyone unmute and tell me what is the area of the plate given in the problem?
1 meter
It is
square.
unit, 1 meter square. So no need to write divided by 1 also. It's nothing but 0.707 W divided by 1 equal to 0.1 Newton second per meter square mu value. Velocity is 0.5. Distance is 1 mm. That I'll convert in meters. So converting the mm into meters, you know, have to multiply by 10 raised to minus 3. Now one can find out what is the W at 45 degree of 1 meter square plate which is flowing on the surface of the liquid. How much may be the weight of that plate? So just check whether the answers are correct what I have written here. W equal to multiply 0.1 into 0.5 divided by 0.707 into 1 into 10 raised to minus 3. So using calculator, just check the answer whether it is correct or not. Okay. So I'll repeat once again this problem. What we have done? We have taken two plates. One is fixed, one is moving. Both plates are at an angle of 45 degrees. This is a special case, angle 45 degrees. And it's moving downside because weight always acts downside because of the gravitational force. And in this problem, using this velocity, viscosity, distance between the plates, angle or area of the plate, one should find out what is the weight of the plate. That's all. Now for that, 45 degrees given, it is with respect to adjacent and hypotenuse lines. So once one can write the force as the force applied by the plate in the inclined direction, I can write W cos theta. The direction in the inclined side what is shown, that is nothing but the force applied by this weight of the fluid. So W is not known, but I can write cos 45 value. Once this is known, I will take the Newton's law of viscosity, that is F by A equal to mu into du by dy. In this formula, if I substitute all these values where W is unknown, and by just transferring the terms in left to right side, I can find out the W, which is around 70.72 newtons in SI unit. So that weight of the plate is 70.72 newtons. All of you understood the problem, how we solved it? When I start searching the names, everyone will say yes. Okay. So we'll see the next problem. In this problem, dynamic viscosity, same viscosity again, dynamic viscosity of oil. See, please everyone also follow the problem, understand it, or if you want, you can write down and check the answers by the equations, how you are finding it, whether the answers are correct or not, or you just copy down so that you can understand the problem, how to solve. So in this problem, they have given dynamic viscosity of oil used for lubrication purpose between a shaft and a sleeve is 6P. So 6P, if it is given as a viscosity, whether it is 6 Pascal or 6 poise or what, can you reply me? What I have to assume? Poise? Yes, very good. So if only P is given or with respect to viscosity it is told, you have to assume it as 6 poise. 6 poise. The shaft diameter is 0.4 meters. So we are lucky that dimensions are given in meters directly, no need to convert. Diameter of the shaft is 0.4 meters and rotates at 190 rpm. See, until now we discussed the speed in the linear movement, meter per second, all the values in the linear movement. But in this problem, if you see, shaft cannot move in linear direction, but it has to rotate between the sleeves of the hollow cylinder. A shaft, solid shaft is there. It is rotating in between the hollow cylinder with a lubricating oil that is rotating at 190 rpm. Now calculate power lost. See here, there is no relation between Newton's law only. Something else is given. Calculate power lost in bearing for a sleeve length of 0.09 meters. So whatever the sleeve length is there between shaft and liquid, that sleeve length is up to 0.09 meter, where the liquid or the lubricant is coming in contact. That area we need to consider. So length is given, area is not given. So area we need to find out. So that length of connection is between the liquid and the fixed plate is 0.09 meters. And for this distance only, we can calculate the viscosity between a shaft and the lubricant. That is 0.09 meters. Thickness of oil film is, yes, thickness is given, that we can consider it as y. Y distance. Thickness of the oil film is 1.5 mm. So again, convert this 1.5 mm into meters. Now analyzing this complete problem, I can sketch the figure like this. At the outside, there is a hollow cylinder or a sleeve, inside which a long shaft is running at an RPM or high speed RPM, 190 RPM. And between the shaft and sleeve, the contact length between the sleeve and the oil, or the shaft and the oil, if you take at a given part, it is 0.09 meters. And the diameter of the shaft given is 0.4 meters. And liquid film, or the thickness of the oil film, is also nothing but the diameter only. It is around 1.5 mm. Means, see here, thickness of the film of oil means you need to consider at any one distance, either upper side 1.5 or downside 1.5, any one. That is 1.5 mm. So here RPM is given. When they are asking power loss, means we need to use some different formulas itself. So anyone can recall any relation which relates RPM and power loss? Just a try. Can reply. The relation which relates speed in RPM and the power loss P. Okay, what I can do here? So as you know, 6 points is given. I'll just multiply by 0.1 to get it in Newton second per meter square. Then area of contact. Area of contact, if you see here, length is given. Area, if you see, it is the hollow cylinder area, the surface area of the inside cylinder. That is pi d L. Pi d is the perimeter of the cylinder. Throughout the length, if I consider, that becomes the contact area. The cylinder which is in contact with the oil for that given distance, that is pi d L. So area is clear, I think, for this hollow cylindrical area, or the surface cylinder area also, if you take, it is pi d L only. Pi d is the perimeter, ring is pi d, L is the cylinder, total cylinder surface. So it is inside. So I'm taking diameter as the inside diameter, 0.4 meters. L is 0.09 meters. So one can find out what is the contact area of the oil and sleeve. That is coming around 0.11 meters per year. And as I told you, the relation between the power and the speed, because they are asking power loss and speed is given. We don't know torque also. So what you can write? 2 pi nt by 60. So for all the rotational shaft equations, if you see anywhere where the power transmission is possible, so everywhere the power lost or the power transmitted by the shaft, you can take this equation, 2 pi nt by 60. So 2 pi nt by 60 is nothing but n is in rotations per minute, that we need to convert in seconds in SI unit. So we are dividing speed by 60. And this is the torque. Torque is force applied for a given radius of the shaft. The torque available on the shaft is nothing but the force available in tangential direction from the center of the shaft, F into R. I can write later, I'll show it. So that is the torque. And why we are dividing by 1000 here? It is not to convert any values here, but we are dividing by 1000 here. Any answer? If I divide by 1000, what will be the issue? Yes. Okay. So what are the power we are finding by 2 pi nt by 60? It is in watts. If I divide that watts by 1000, it will be kilowatts. Always we talk the power in kilowatts. So to convert it in kilowatt, I am dividing by 1000. Or can leave as it is, 2 pi nt by 60. You can write in watts also. Both are same. Now from this RPM, we can calculate the velocity of the shaft, which is in linear meter per second. So that is also again pi d n by 60. I think this you have studied, 2 pi nt by 60 or pi d n by 60 in EME. Yes, elements of mechanical, have you studied? Ajit Kumar. Ajit Kumar is not attentive. Anish, yes. Lokesh. Ajit Kumar is not attentive. Yes, now he is attentive. You have studied, no? That pi d n and 2 pi nt formulas. Okay, if you have studied, no issues. So this pi d n by 60, I can write such that diameter of the shaft is known, Then RPM is known. So I'll convert that into RPS. So once you take this equation, I can convert this RPM into meter per second, because we left with diameter in meters, then RPM to RPS. So seconds you can write directly. So now I have got the U value. So U value is around, how much you got there? U value is 3.4. I'll take 3.4 meter per second. Now we got velocity value. Okay. Then viscosity is also given. Y is also given in mm. We can convert it in meters. And by this equation, tau is not known. So I can write directly tau by substituting all these values. So viscosity is how much? 0.6 Newton second per meter square. So this is found out here, 0.6 Newton second per meter square at the top. U is the velocity in linear, 3.4 meter per second. Distance y is 1.5 into 10 raised to minus 3 meters. So once you substitute all these values, I can find out the shear stress, what is applied or what is there in the liquid surface, which is in contact with the shaft. Because shaft is rotating, that is trying to overcome the resistance of that liquid, or trying to overcome the rings of that liquid cylinders, or liquid is rotating in the cylindrical form, cylindrical layers. So there is a resistance between all the cylindrical layers between shaft and the sleeve. So that resistance it is overcoming. So answer is around 1.59 or 1.6 into 10 raised to 3, or 10 raised to 3. What I can write here? Can you tell me? 10 raised to 3 Newton per meter square. What I can write in other form? I can write it in, yes, Newton I can convert in kg. That is also there. But we are preferring Newtons in SI units. So I can also write 1.6 kilonewton per or kilonewton per meter square. Correct? 10 raised to 3 is kilo. Yes. Then what is the question? We have to find out the power lost. Here, calculate the power lost in bearings of the sleeve length of this. Only power lost if you find out is over. But to find out the power lost, we need to find out all these equations. This is the power available in the shaft, not power lost. The earlier power what you have taken, this is the power available from the shaft that we got. But here also torque is not known, only RPM is known. Now we'll go for the torque. How much is the power? So now if I go for the torque, I can write the torque as F into R. So you assume that one circle is there here, the cross section of the shaft, and I know the radius of the shaft, and tangential force applied to rotate the shaft. That is the force, minimum force required to overcome the resistance of the lubricant oil. Okay, so that I can write it as torque required to overcome is force into R, because we need torque in the power, minimum power required to rotate the shaft. Okay, in that case I can write it as force. Force is how much? Force is how much they have given. They are not given, but force per unit area I can write it as tau itself. In the earlier problem also we have seen. Shear stress is nothing but force per unit area for the liquids. So I have taken this 1.59, sorry, yes, 1.59 into 10 raised to 3 Newton per meter square. But area of the sleeve is also known. What is the area of the sleeve? We have found out pi dl. Where it is pi dl here. The area is 0.11 meter square. So if you multiply these two values, one can write the force like this. So force is equal to 1.6 kilonewton per meter cube into 0.11 meter square. That will give us 175 newtons. So radius of the shaft is known. because they have given the diameter of the shaft. So diameter of the shaft is 0.4 here. Radius of the shaft is 0.2. So here we have taken the 0.2. So 0.2 into 175.01. The torque is required is 35 Newton meters. Force is in Newton. Radius is in meters. Now we'll find out what is the power or the minimum power required to rotate the shaft and to overcome the resistance of that lubricant between the sleeve and the oil. That much power is lost actually. Okay, that much of power, minimum power, will be lost between lubricant oil and the cylinder or the shaft which is rotating. Now, if I rotate the shaft above this power, what will happen? The shaft can supply the power to one end to the other end with this loss, because I am supplying more power on the other side of the shaft from the motor or some machine. Then I can transfer it to some other machine. But minimum power should be how much? This much. So that minimum power, how much is lost or how much is required to just to rotate or to overcome the resistance of the liquid itself, that we are finding here. So now we know torque, RPM, RPS is also known. So you use these all terms in this 2 pi nt by 60 into 1000. So if you take all these terms, I will get the power lost or the minimum power required to rotate the shaft is 0.6964 kilowatt. Or as I told you, you can write in watts also. It will be 696.4 watts. This is the minimum power required. If I supply the power of 695, what will happen? Just less than this power. What will happen? You just reply. Yes. It will not rotate only. You cannot rotate the shaft. If I supply lesser than this value, 696.4, whatever the value is there, if I supply less than this, it cannot rotate only. Because minimum power required is this much. And if I supply more than this also, this much of power is lost to rotate or overcome that resistance of the liquid. I hope these points are convincing to you. Let's repeat once again. Okay. So what we have found out is the total power, okay, is 0.6964 kilowatt as per the relations of this viscosity, shear stress, torque, and rotation speed, diameters, everything. This is related with respect to power required to rotate the shaft with respect to that overcoming the resistance of the liquid. This is the shaft rotating here. Shaft rotating in between sleeves or in between the liquid layer. So to rotate this shaft, we need some force or some extra power is lost. That minimum power, whatever is lost to rotate that shaft is 0.7. Almost we take 0.7 kilowatt nearly. Means if any time if I apply the power less than this 0.7, I cannot rotate the shaft because resistance of the liquid or the viscosity of the liquid itself is more than the power applied. I cannot rotate. But whenever you apply the more power than 0.7, say for example 1 kilowatt if I apply, 0.7 kilowatt is lost in the rotating the shaft or overcoming the resistance of the liquid itself. Then remaining 0.3 kilowatt is supplied from one machine to other machine. Now it is clear? Okay. So now the time is almost 11:50. We'll stop the class today. So next class we'll take some more problems on the viscosity and we'll discuss some more properties of this fluid in the first chapter. Okay. Thank you.